Hi, this is going to be a quick talk on a small hack that I just did. We hosted like a small hackathon, and this was the project that I chose to work on. So this will be finite field implementations of Barrett reduction and Montgomery reduction. This is based on a small presentation that RISC-0, a zero knowledge proof company, did. This is my first time using Rust. I limited my time to 10 hours. And so at the end, I'll kind of go through what I've done. Not all of it got completed, but first just wanted to outline exactly what the topic was and sort of what was being aimed for. So this is finite field implementations. So fields here refers to fields in group theory, has some members closed under two binary operations. Addition and multiplication being what we're using here. This is a way to more quickly add and multiply numbers when you're working within modular arithmetic. So the number that you're holding onto is always modulo some modulus. And you might work with numbers that exceed normal word size, word here being how many bytes or how much information can be held onto on typical architecture. So most computers would, for example, hold 64 or 32. And so you have big ints that go past that, but then becomes an issue because you don't have them constant size. They're like unbounded and they have to be on the heap and stuff like this, and that becomes a big issue. These two techniques are trying to deal with division being really costly. So if you're making use of modular arithmetic for something like a ZK proof or some other cryptography that you're doing, you want to be doing lots of the two operations, addition and multiplication, and then reducing often. And the naive way to reduce includes division. And so Barrett and Montgomery are both alternatives that don't do that and aim to speed up the process. The other interesting thing that was aimed for and is sort of relevant here, a flavor of side channel attack. So side channel is if a program or anything in the world puts out additional information that isn't really about it doing its main function, but something like how much heat is generated or how much time there is between operations, anything like that is a side channel. And you can have side channel attacks that take advantage of that. So for example, if I know you have one of two passwords and one of them is really long and I see you typing for a really long time, I think like, oh, you must be using the really long password, for example. That's like a very cheap example of a side channel attack. That's a timing attack. And similarly, if you're doing something with a key or a hash, and I can derive some information from how long it took you to return something to me, then you are at risk of your security has been weakened in some way. So another thing that we're aiming for is constant time operations to avoid timing attacks. So when you add and multiply, when you reduce, it shouldn't be variable time based on differences in the input. Bringing that over into tests that I attempted to write at the beginning. This was also my first time using Rust, so some of the tests that I wrote didn't really make sense based on how I had to implement things, but we want modular arithmetic to work for add and multiply. You can reduce naively, which is the way in which you use division, or with Barrett or Montgomery. And then we want to test add and multiply on numbers that would overflow. So numbers we're probably going to be using are like unsigned 64, and if they go over that size, this is like a case that we might come into, but we want to be able to handle that without an error. And then benchmarking naive versus Barrett versus Montgomery. for example, repeated addition or multiplication, to see how the different ones perform. And I also wanted to bench each reduction for different sizes of inputs, or in general different inputs, to see if we could address some of the timing attacks. That is all that I wanted to present on the whiteboard. Now we'll hop into the code itself. Jumping into the code, again, I'm new to Rust. There are many ways in which I probably misuse or don't understand all of the features of this language, particularly inheritance, and some of the structuring, I guess, just looks very much like a hacked project. As the project grows, would change, certainly. So you have your two binary operations that this finite field would define, and then you have, I believe I stopped using this trait, but you're also going to have different forms of reduction. And I chose to have the main class that we're working with be modular arithmetic. It has a value and a modulo, and then it has some reduction function. So you could make one of these that has a naive reduction function, or one that has a Barrett reduction function. And when we get to Montgomery, it seems that some changes to this should actually be made, because it maintains a separate variable in order to be able to repeatedly do operations cheaper. And one of the drawbacks of Montgomery, I guess you could say, is that it's hard to get back to classical form. If you need to get to classical form all the time, you might make use of Barrett instead, but we will get to that later. So add, you're going to be taking something that has a value and a modulo and a reduction function, and then some other value. So this is starting to get into the overflow thing that we're trying to address. You can take each of the values and break it up into words. Because, for example, if you had two max size values and you added them together, they would overflow, right? As soon as you go one past max, you have overflowed. And when you add two things, you are at most going to double, right? 2 max is certainly over, but if we broke each of the values into 2 different words and then operated on them in that way, we would be okay and we wouldn't overflow. So WS is going to be what we return. It's the word, or it's the result of this operation. This is similar to math that you might have done in elementary school, and similar for the multiplication. And so the number of words that it has is going to be 1 larger than for each of the inputs, right? The inputs we're going to break into their 2 words, but then the result might overflow. And so we're keeping an array. And then, so this I generalize in multiplication, but this is essentially just the process of breaking it into words. We are taking something that's 64 bits and shifting 32 over and then back 32. This, I guess, depending, could overflow. But if you ignore that, I guess I don't know, like some compilers might treat this differently. So the way that I do it below in multiplication might be better to go off of. But essentially what we've done is we get the 2 values, each broken into 2 words, and then we're going to iterate over them. I'm saying that the result will be, so this is the way that modulo happens in Rust, it turns out. The result is the ith word of the first input, the ith word of the second input, and whatever carry we're holding on to. And carry will either be 1 or 0. And I mean, the first time that we see it, it will be 0. But then as we do this more, you might have a carry bit come over. And then the very last word will be any carry from the highest order operation. And then reduction happens in this step. And based on what reduction function we've passed in, we are going to get something different. What we have to do is take advantage of AB mod n being equal to this. So if we don't take advantage of this, I guess this is multiplication. Yeah, okay, that's right. So we have the value that's in the result word, and then we have another number that's just trying to byte shift it over to the correct position to return it to classical form, I guess. But this might overflow, so instead we do A mod n, which won't overflow, right? A is not larger than max, B is not larger than max, and then we multiply these two things together. And how high could this be? Well, this could be n minus 1 at max. And in such a case, that would be an issue, wouldn't it, if we have high enough modulo? So maybe I just haven't tested for that case. Our modulars are always going to be prime. Do they have to be less than square root of max? I'm not sure about that. There's probably, for like a correct implementation of all of this, there's more finagling that needs to happen. Or maybe we just don't work with unsigned 64, but I think the point of this is that we are getting away from big ints by creatively doing operations here. Regardless, we're making use of this in that we reduce first the ith word of the result by the modulo, and then we also reduce the byte shifting that would happen by the modulo, and then we reduce that whole thing because we always want to keep it mod n, whatever n is, and then that's returned. So I could get into multiply because I think it better, this was done first, and then multiply better generalizes some of this stuff. This has now been done. I, just for convenience sake, said that the word size would be a byte. And then I'm making a number of arrays. This is for the first input, this is for the second input, and the max size that it could be is twice n. Right, when you added, you could at most double the value, but that only takes up one more bit of space. But here, when we multiply, you could square the value, and so it takes up twice as much space. And then we're populating the arrays with the structure that we've passed in. And here we're doing, so we're right shifting to get rid of the right bits, because you have something like, you have some number, and the first time you just want to get that part of it, right? And then the second time you want to get this part of it. So we first right shift, cutting off that, and then we are going to mask, which I think is the correct way to do this. So you're doing byte and with something that looks like, well, this is base 10, so this is not exactly correct, but something like this essentially, right? Like these all go away because when they and the bottom, the other number, 2 to the 8th, doesn't have anything there, and then you're just left with this. That's how we first set up this array of words from our input. And then we run through doing multiplication. So you again have a carry. You are running through all of the words. Some of these words might have 0. I think implementations of this that I've seen, one of them has length n, one of them has length m, and you do the larger of those two, but here I'm just saying, well, I know that 64 is the largest that it will be, divided by whatever my word size is. So if one of the inputs, if the first input has a 0, then we know that 0 times anything is just going to be 0. So we can skip this. We don't need to, I don't think, but it might as well. And then for that word, we look at each of the words in the second one. Again, this is how you do modulo. This is pretty understandable and has been seen before. So this is one of the areas where I didn't finish and is difficult to do, so I'll try to explain what's happening instead. So after you have your resulting word, ws, this array of words, right? So if your result would be something like this, but this is too long, then you break it up, and your array looks like that. But then you need to be returning something that's not overflowing, and you have a modulo that you're working in, and so you should apply that, and that will reduce it to a form that you can work with. Or if you're doing Montgomery, I believe you still reduce, but you're keeping this other piece of information, which it allows the number to still be not overflowing, as long as you keep this auxiliary information and continue working in that system. Special case for classical. Okay, so what we have again is some series of words like this, and the reality is that it's bytes, so it's base 2 is how we're thinking about it, but I'm just showing it in decimal because that's easier to think about. Right, so you could think of this as a series that you are adding together, and result equals the sum of that series. And that series is, well, first it's 47 times 100 to the 0, and then it's 1 times 100 to the 1, and then it's 86 times 100 to the 2, right? It is a sum of terms like that. And if we take mod of a series, okay, so something like a plus b mod c, we know is actually, God, I feel like I need to check this. If we have something like 2 plus 2 mod 4, wait, why am I messing this up? It's absolutely, okay, mod of a series is the same as that series with each term modded and then the whole thing modded, right? Because you could have something like this, and you can't just mod each term, because then you'd end up with 6, which is greater than 4. So you again have to do that at the very end. How long until this would overflow? Well, it depends what size this is in relation to the max of the data structure you're using, right? We know this is going to be less than U256, no, U64 max, but we don't know if you multiply it by 10, for example, like maybe it's within, it is more than 1/10 of this max thing. So you might at some point need to repeat this, like do it every time. And I didn't get this far within my time, but this is the next consideration, I feel like. But essentially, this is like the byte shift component, and then no. Okay, so starting, we just do mod of each term. And then what is each term? Each term is a value that is of the word size and is some factor of 2, considering that my words are bytes. And I could take advantage of what I mentioned above, that this is the case, in an effort to not overflow. But we might still end up in trouble because these factors of 2 can get very large. So instead we're again thinking, well, how can I do this iteratively to not overflow? So b is our factor of 2. Instead of saying it is 2 to the n, I could say it's 2 to the x plus y, where n is x plus y, and then I could represent it this way, and then I could again apply the above. And essentially, within here, we're repeatedly reducing using whatever reduction function we're given. And that's the next thing that I'm going to get into. But once this is figured out such that it doesn't run into any cases of overflow, multiply works ostensibly. And I believe from reading that Montgomery does something different here. Because you can also, within this loop, be doing reductions. So let's jump into some of the reductions. This is naive reduction. You get some quotient, which you have some value and some modulo, and it's just division. Because these are integers, it's taking the floor of it. And then it's fair to say that reducing the value so let's say you have some number that is larger than the modulo. If I subtract the modulo any number of times until I've gone negative, I am doing something correctly. So I could instead just loop repeatedly subtracting the modulo. And then I would eventually have a number less than the modulo, and I would return that. Instead of doing that, we know that the number of times that we would be looping is this q value. So we would be looping 5 times and maybe a half more. And the half more is modulo times our, modulo times a half is equal to our value, right? But we just want to be returning that extra bit. So this is naive because it uses division, which is expensive for computers, classically. I say classically, like I believe in all cases with present technology, it's difficult for computers to divide compared to things like add and multiply. So what we want to do, Barrett's contribution, is that we could instead be, okay, so instead of doing something like value divide by mod, that's going to be confusing. Value divide by mod, we could instead say value times some number. Now, what is that number? That number is a top and bottom. So it's some value on top, and then some power of 2 on the bottom, right? Because dividing by a power of 2 just means right shifting, and that's pretty cheap. But how do we figure out what is on the top? To get that information, we need to, regrettably, do some division. But we can pre-compute for a given modulo. What I've done is kind of mock that experience. I don't exactly know how this would be implemented. So for every modulo, there's some value of k, and I believe there's some value on top, but I might have my variables a little bit off. And this pair, m and k, for given modulo, can be pre-computed, right? And you could pre-compute all of the ones that you might expect, and then hold on to that somewhere. The way that I've done that is to just have a hash map with a couple that I'm going to test. The modulos are all primes, so I just chose some like fairly large 7-digit prime as the main one that I'm testing with. 500, not prime, but I had that too. I believe that it's prime just because cryptography typically works with primes. I believe that you can do like clock math, finite fields, modular arithmetic with non-primes. I don't exactly know the culture around it or why it's chosen or not chosen. But okay, getting into Barrett reduction. We are going to approximate division by n by multiplication by m over 2 to the k. So I got that part right. M is the floor of that. So what was I saying? I have value divided by mod. What I really want is the floor of value divided by our mod. I am going to take this away for a second and say that I think the form that I want that in is value times number times some number, right? This will be good to work with if x is of the form m divide by 2 to the k, because then we're just bit shifting. Okay, how do I get there? I can divide, get rid of the value on both sides, and I have 1 over m equals m per 2 to the k. I can then say, well, my mod m, big M, is 2 to the k divided by m. But what I wanted was m, the small m. This is a little bit confusing. 2 to the k divided by my mod. Right, again we have to do division, but we only have to do this once, and then we can make use of it for all future calculations, not just with this struct, but like in general. How are we choosing k? So k has to be, we're choosing a k such that 2 to the k is less, or is more than n. So you can think, well, the smallest that would have to be would be k is more than LGN. So I take my binary log, LG means binary log of n, and I'm going to get some number. And then I'm going to take ceiling of that, and that is the smallest such satisfying. Is that correct? No, I believe it's floor of that. Right, and then you could have less? Wait. I thought that I knew this part. I'm computing an m that is equal to 2 to the k divided by n. We're doing the division once, then we map from the modulo to pre-computed k values. So here I had 500, I took LG of 500, and I got something like 256, 256 is the one that I would have. Okay, this sort of matters. I wanna get this right. LG of 500 gets me this. So I could say if my k is 9, then I can compute my m, right? I have my k, I have my n, I can get my m. But I instead chose to do a larger one, 20, and this was something that I'm not clear on. Maybe I find it out through experimentation, but it's not clear to me how to choose a good m. I was at first choosing the smallest, and that didn't appear to be right. Again, when I did this process, I did binary log of this number. I said, okay, 23 is the smallest that I could have, but I'm instead going to use 40, and then just plugging in numbers here to this equation, I got this as my m value. That's all to say, when you do Barrett reduction, so as you're adding numbers together, as you're multiplying numbers, you need to reduce in order to not overflow. And you're doing all this in modular arithmetic, so you have some modulo. And it's always fair for you to reduce to that modulo, right? You have like 300 of your modulo. Let's say your modulo is 7, and then you have some extra amount, right? And it's always fair for you to cut that off. And that's what this reduction is doing. So let's see how this gets used in practice once we have our pre-computed values. Here I'm just checking that for the given modulo I have it. And if not, there's some issue, but that's just an issue with how I've implemented it. We get the quotient, which is whatever value times the m, right? M is 2 to the k divided by n. And then we shift over by k. And that's essentially saying, get rid of this part. Okay, so what we really have is value divided by n, and that's approximately it. And then the result will be, you have your original value, which is something like 5,000, but I have a modulo of, let's say it's 5,020, but my modulo is 100, right? That's actually just 20 plus some number times my modulo. And so this is here, and then I take away this part. That's what's happening here. The way that this ends up working, and there's a larger justification for why, what you will get will be in the range of inclusive on the bottom side up to 3n. So n is your modulo. And then you might have to a couple times subtract away the modulo. And you'll end up with something that's in the range that you want, which is 0 to n, non-inclusive on that side. And then you return that. So the Montgomery, I did not fully understand and did not implement, but possibly I will return to this and finish that up. At the very least, I'd like to understand better why Montgomery reduction works. The Barrett reduction feels pretty, like even when it's just presented in 20 minutes, this sort of makes sense, right? None of this is crazy. You just do this division one time and then get to use it in the future. And like it makes sense that bit shifting is the cheap way to get around doing division. So this is just about how I ended up structuring things. I at first made 3 different classes, but eventually came to, well, all of these things are modular arithmetic. They have a value, a modulo, and some reduction function. And then down below, so ideally this would be separated out into another test file as things grew, but these are different testing modules. Just checking that modular arithmetic works for some of the examples given in the slides. And then checking Barrett, and then doing benchmark tests. So you, some number of times, with random numbers that you're generating as your inputs are going to, and you have some modulo that's a prime number that you've already pre-computed your k and your m for. You're going to just repeatedly do operations and then see, is it cheaper? And I have slightly disappointing results, but first let's break out into what things we are benchmarking. So naive addition, we are adding using a naive reduction function, and we're doing this repeatedly. And then you have Barrett addition, which uses a different form of reduction. And then we're seeing, well, if I do this with just small numbers that might not need to reduce in the same way, or it might be less costly in their reduction function, what I would like to see is that this takes roughly as much time. It is indistinguishable from normal Barrett reduction. Actually, this is the naive one. And then we have, okay, so there's just, you have naive and you have Barrett, repeated addition, and then you're seeing, well, if my numbers are always smaller or easier, I would like to see it taking roughly the same amount of time such that someone couldn't distinguish what I'm working with. This is addressing the side channel attack, the timing attack. I believe you can see this run. So it's fast multiply. Is this the one that has it? Okay. Yes, cargo bench. So let's just focus on what this is telling us. What we set it up to do is 100 times do the following thing. Create these two numbers, add them together, and as a part of the add, it will reduce them down such that they are within 0 to their modulo. And here that we see that with Barrett adding small numbers, it took slightly less time, and I believe it consistently takes slightly less time, which I imagine that some other work has to go into ensuring that reduce gets called regardless of whether it's actually needed, and from a very atomic level, like the same number of operations happen. But as it is implemented now, it is noticeably less time for adding small numbers. And then you see naive addition and reduction actually takes less time for my implementation than Barrett. So let's try to consider why that is, what might have gone wrong. The only part that's different, right, all of this add stuff happens exactly the same, and then you get here. And you are, well, so the way that we've simplified this is twice. For each add 2 times, you are doing this. For each add 2 times, you are doing 3 reductions. And these are just different callbacks. So for this one, it uses naive, and for the other one, it uses Barrett. So you have like 100 times, you are 2 times, calling this 3 times, right? And it seems that naive goes faster than Barrett. Let's try to figure out why. Printing, I probably shouldn't be printing. And then you have division, right? And ostensibly this is really expensive and makes things hard. And then this is trivial. I believe this is done in both. Or, no, it isn't actually done down here. And then what do you have here? You create a hash map. And I think if I knew Rust better, I could have this outside somewhere and accessible. This could be a constant, I guess. I'm not exactly sure how Rust handles these sorts of things, but we don't need to instantiate a hash map each time. I'm just doing that because I sort of have to. So maybe that's a big deal. Then we're matching on the result. This is probably pretty cheap. It is, I'm not sure if this is the wording in this language. It is an option with a tuple in it. Matching on that's easy. So here, not an issue. It seems to never get hit. Here, we're again printing line, which might throw things off. I'm not sure how it gets handled. I would expect that it just doesn't get run. So what are we doing? We are multiplying and then shifting. These things are cheap. We're doing the same thing that was done in the naive. This isn't actually code. And then maybe we're doing this once or twice. So if I had to guess, this is an issue. I believe that my implementation is good enough that Barrett should be faster. So it's probably that we're creating a hash map. Why would that be so expensive? When we make a hash map, its variable size needs to go on the heap, I would think. Right? Looking up in the hash map is cheap. Okay, so you have a hash map. It has some buckets, and each of those buckets contains something, a tuple, which is fixed size, right? It's U64, U64. But the hash map has to be, like, how would it know how large it needs to be? I think that it needs to be variable length. And as a result, allocating it, like, that's a size issue. Allocating it might take more than division. Going from an array to a hash map might be costly. Maybe? Huh. It's definitely in here. It doesn't seem like it would be anywhere else that we experience slower speeds. We're also, each iteration doesn't get to see other iterations. So it's not that some effect is accumulating. But anyways, these tests hopefully highlight what we were hoping for, what I was hoping for, I guess, as the person who programmed this. And the results don't seem to support that Barrett is better, although it could be that it's only better for larger sizes or more. Okay, let's think about the sizes of things that we put in. We're putting in something random in the range of U64. So that's, I mean, the average is half of the max. How do we feel about that? We think that Barrett is better than naive exclusively because it doesn't do division. That's the claim. And the division has to happen regardless of the size of inputs. And even if that weren't the case, what we're working with is on the order of max for this data structure, U64. So it's not reasonable for me to say that what we're seeing is because we're not working with things big enough. Okay. Anyways, this was the 10-minute hack that I did. No, sorry. This was the 10-hour hack that I did. I learned some Rust. I learned more things about finite fields, modular arithmetic, Barrett reduction, and a little bit about Montgomery reduction. Hopefully, I will have time to go back and do more work in that direction. I would also love to ask some questions of probably specifically Risk0, the company, about some of this, because there are, I think that I exit with a little more questions than I had before. But I hope that you learned something. If you have any comments about either how I make use of Rust or the specifics of this sort of work, happy to hear those. I think this sort of thing felt useful for me to put out there, largely because these sorts of topics you just don't really have great access to materials sometimes. Although I did find a lot of good explanations of this work, and I think much of this is pretty low-hanging fruit math-wise, but it was fun to see it implemented and come to some sort of fruition. Thanks for watching. My name is Kai.